Ladies and gentlemen, my name is Minvydas Ragulskis from Kaunas University of Technology, Lithuania. I would like to thank the organizers of the first online conference on nonlinear dynamics and complexity for inviting me to read the presentation entitled Clocking Convergence of Discrete Nonlinear Maps, including Fractional Maps. This is the outline of my presentation. I will give a short introduction to my research group, and then I will introduce the H rank of a sequence and how we use this rank for defining the complexity of a transient process. Then I will continue with the non-invertible logistic map and explain the non-asymptotic convergence. Finally, I will switch to invertible bouncer system and explain how and why non-asymptotic convergence can exist in this completely invertible system. And at the end of the presentation, I will focus on fractional difference logistic map and show the existence of a shadow of the manifold of non-asymptotic convergence in this map. And I will conclude with a discussion. Lithuania is a small country in Eastern Europe, and it's a beautiful country with a long seaside. This is the history, the turbulent history of our university. At the moment, we are the largest technical university in the Baltic states. And this is my research group, some of my PhD students and the students who have completed their degrees under my supervision. The rank of a sequence. If we consider a scalar time series, the Hankel transforms this sequence into a sequence of determinants of Hankel catalectic matrices. The H rank of the sequence S is equal to M if all higher determinants are equal to 0. This property must hold up to the size of the determinant when the size tends to plus infinity. The last determinant, which is not equal to 0, marks the rank of the sequence. The definition was coined in 1995 by Kurakin. And in fact, there are many links between the definition of the H rank and the properties of the Prony approximation, which is a natural extension of the Fourier analysis. How we can reconstruct the mathematical model which governs the evolution of the system? Well, we need to construct the Hankel characteristic equation. Note that the characteristic values, ρ, are placed in the last row of the galacticon matrix. Using this mathematical technique to reconstruct the complexity and the mathematical order of the model, we are able to define and to approximate different processes, including chaotic processes. Making a step further, we define the concept of epsilon H pseudospectrum. Please note the difference between matrix spectrum and H spectrum. Now we are dealing not with eigenvalues, but with raw values, the characteristic values of the galacticon matrix. And when we perform perturbation, this is different from the ordinary matrix perturbation. We are perturbing not the elements of the matrix, but the elements of the sequence. And when doing such kind of perturbations, we are able to tackle chaotic time series contaminated with external noise. So we can approximately define the age order, the complexity of a time series. And here are some examples when we discuss how the external noise can contaminate the data and can contaminate the model which we are trying to reconstruct. The logistic map. It's completely clear that the map is non-invertible. If we want to make one step backwards, we need to solve the quadratic equation. So each time we are trying to move back in time, we have an option of two choices. If the parameter A is placed in between 1 and 2, it's very well known that the stable fixed point x0 is 1 minus 1 over A. And naturally, if we are trying to solve the quadratic equation, as I just mentioned, we produce two roots. And one of the roots coincides with the fixed point itself. It's marked by a white circle, but the other one is the black circle, and it denotes a terminal point. We cannot move backwards any further on because all roots will be negative, and any movement backwards is impossible. However, if the parameter A is placed between 2 and 3, the fixed point is still the same. It's still period 1, stable orbit. And if we start from this point, naturally, we have the period 1 orbit, but we can move to another white circle, which splits again in 2, and the number 1 marks that we made one step backwards. Then making another step backwards from this white point, we move to the terminal point and to another black point, another white circle, and we move backwards in time, producing a number of terminal points and a number of white circles. It's quite easy to reconstruct the dynamics of the logistic map until the moment when the parameter A is less than 1, the stable fixed point is equal to 0, and then it tends to 1 minus 1 over A, and here's the pre-image of the stable fixed point. So the stable fixed point is denoted in a dashed line, and the thick black line shows the pre-image, the first pre-image. When the first pre-image intersects the stable line, this is the moment when we have the bifurcation. It's the homoclinic bifurcation, and the infinite number of pre-images is generated right after that bifurcation. So the thickness of the line denotes the number of the pre-image. So if we return back to this image, we can see that this is 2 steps backwards, 3 steps backwards, 4 backwards. The number of points is infinite, but countable. And at 3, we have the period 2 bifurcation and the pitchfork bifurcation, but I do not plot it in this map. I just wanted to show this complexity of pre-images for the period 1 orbit. Now, we compute the H ranks, we reconstruct the mathematical model of the transient process, and we are able to determine how complex is the transient process. And you can note this is the period 1 orbit, which is stable until 3 and then becomes unstable. This is the period 2 bifurcation. And this is the homoclinic bifurcation. And these are all the pre-images. We can clearly see the number of the pre-images in the pattern of H ranks. So what we can observe here, all are intertwined manifolds. The stable manifold, the unstable manifold, and the non-asymptotic manifold I am just going to talk about. So if this is the period 2 bifurcation, this is the stable period 1 orbit, this is the stable period 2 orbit, the period 1 orbit becomes unstable after when the parameter A becomes equal to 3. And these are the pre-images, the number 1 pre-image, the number 2 pre-image. So this is the non-asymptotic convergence from the stable manifold and non-asymptotic convergence from the unstable manifold. So taking a closer look to the paradigmatic logistic map, we may observe 3 different kinds of convergence. The first one is asymptotic convergence to a stable period 2 orbit. Please observe that we are working at A equal at the region where the parameter A is equal to 3.3. This is the area where the period 2 orbit is stable. So we are starting from some initial condition, and we asymptotically converge to period 2 orbit. But this is not the only way how we converge it. We can converge it to it if we select initial condition in the deep trench of the second pre-image. So the second pre-image shifts the coordinate to the first pre-image, and then we approach the period 2 orbit non-asymptotically in 2 time forward steps. Please note that the number of forward steps until we can reach a stable orbit, it totally depends on which pre-image we are placing our initial condition. And finally, non-asymptotic convergence to the unstable fixed point. At this number, you please remember that at 3 we have period 2 bifurcation. So period 1 is unstable orbit, and if we start from the second pre-image of the unstable orbit, in 2 time forward steps we approach the unstable period 1 orbit, and the system will continue indefinitely running in the period 1 orbit. So finally, we can note that 3 different transient processes exist for the logistic map, for the classical logistic map: asymptotic convergence to a stable orbit, non-asymptotic convergence to a stable orbit, and non-asymptotic convergence to an unstable orbit. What would happen in a map is a completely invertible. It's very well known that non-asymptotic convergence cannot exist in completely invertible maps. It's a very well known. We can prove this statement using the contradiction. Anyway, we continue with the bouncer system, Fermi-Ullmann problem, a particle falling down in a constant gravitational field on a moving platform. And this is a really paradigmatic model of a completely invertible system. This is a completely invertible system. And this is the bifurcation diagram when we change the parameter beta, while the parameter alpha is fixed to 0.1. Here are the H ranks at different values of beta. Please note that this is a 2-dimensional system, so we have 2 different initial coordinates, x0 and y0. So we have 2 different images of the pattern of H ranks. And if we couple all these images when the parameter beta is allowed to vary continuously, the horizontal sections and the vertical sections of patterns of H ranks produce such interesting plots. And what is strikingly interesting is that the bouncer system, the completely invertible system, well, first of all, asymptotic convergence to a stable period 2 orbit. We select the parameter beta, where the period 1 is unstable and period 2 is stable. We can observe an asymptotic convergence to period 2 orbit. This is really completely not astonishing. Anyway, this is much more interesting. Period 1 fixed point is no longer stable. Anyway, in the pattern of H ranks, we observe the similar structure we had observed in the logistic map, meaning that we have a shadow of a previously stable fixed point, and temporary convergence to this shadow is still not very astonishing, but astonishing is the basin of temporary attraction. What's happening? First of all, if we start from this trench, we move from the second pre-image to the first pre-image, and then to the surroundings of the period 1 orbit. And finally, the system converges non-asymptotically to period 1 orbit. But we have just explained that non-asymptotic convergence cannot exist in completely invertible systems. So we cannot outplay the nature. Sooner or later, the process will diverge to the stable 2 period orbit. So we can say that we are able to temporarily stabilize the unstable orbit in completely invertible systems. So this is the graph for x's, and this is the graph for y's. The skeleton structure of the pattern of H ranks, it's really astonishing. That, as I have just mentioned, non-asymptotic convergence cannot exist in completely invertible maps. However, the whole structure, the period 2, the pitchfork bifurcation, the pre-images, the first pre-image, the second pre-image, the third pre-image, the fourth pre-image, and as I mentioned, the incountable number of pre-images, the countable number of infinite pre-images. This is really, really astonishing. Finally, let's focus on a fractional difference logistic map. So on a paradigmatic model of a fractional discrete map. The derivation of the governing equations for the fractional difference logistic map follows from the classical fractional difference equation, where the left Caputo-like delta difference is defined by this formula. And delta M is the mth order forward difference operator. And we are using the classical following factorial to define all the relationships. So here is the governing model of the fractional difference logistic map. This is the well-known and widely used model to describe a discrete map with memory. And it's really interesting to note that the backward memory, the backward observation window, which affects the dynamics of the current state, it reaches the initial condition. Well, we select the parameter nu equal to 0.8. So this is the bifurcation diagram of the fractional difference logistic map. And these are the patterns of H ranks. And you immediately can see that the striking similarity of these maps to the previously discussed figures. Really, if we start from any initial condition and we selected the parameter A equal to 3 when the system converges to a period 2 orbit. And what is happening if we select an initial condition lying straightly on the trench? Well, we can observe the temporary stabilization of a period 1 orbit. Moreover, if we select the initial conditions on different trenches, we have some transients, temporary stabilization of period of 1 orbit, and then eventually converging to period 2 orbit. And if we analyze more carefully the structure of the manifold, we see that the number of trenches is countable but infinite. So it shows a shadow of non-asymptotic convergence manifold in the fractional map. So the algorithms for the computation of H ranks help to visualize the intertwined pattern of the stable, unstable, and the NAC manifolds. The non-asymptotic convergence cannot exist in completely invertible systems. However, the shadow of the NAC manifold is still detectable. The shadow of NAC manifold is also observable in fractional maps. This is a strongly counterintuitive result, especially keeping in mind that the memory horizon goes back to the initial conditions. And the existence of such shadows in fractional maps could help to construct algorithms for temporary stabilization of unstable orbits in fractional maps. Thank you very much for your attention, and I am looking forward for any questions and further discussions. Thank you very much.